Hi there, Feeling Lab with your mate JJ. Today is Learning the Art of Electronics Day. Silly job title for today is Energy Elicitor. Today I'm the Energy Elicitor. So, yeah, it's going to be a pretty quick video today. We're not doing an experiment, not because we didn't want to, but just because I got caught up with an emergency at work today and I wasn't able to get around to actually get an experiment done. But I didn't want to let the day go by without making a video. So what we're going to do today is some revision, which we do every Tuesday. So we'll just go over our notes again, and I have actually added notes since the last time we had a look at them. So let's jump over the computer and do our revision and have a look at our new notes, and then we'll wrap up. Before we do that, check out my new component drawers. This one here in the middle arrived, and I've been able to distribute stuff. So now I've got this one in the middle is for microcontrollers, and the one on the left is for sensors of various types. And there's a whole lot of spare drawers, which is great. I've got some capacity. Anyway, let's go over to the computer and have a look at our notes for learning the art of electronics.
Here on the computer. Now this is the ITL wiki, which is where we keep our notes, and today we're working on learning the art of electronics, and we're working through the second edition. Taking its time to load. There it is. Alright, so let's jump ahead to chapter 1N, DC circuits. Of course, we've seen this before, so we'll just skim through it. We're learning about voltage dividers. The course is about the laws, rules of thumbs, and tricks that constitute the art of electronics. When delivering power to something, the something is called a load. This course is concerned with electronics to model and process information. Particularly, we're not that interested in delivering power to things, but we do have to do that occasionally. The question, is it better to model information with voltage or current? And the answer is voltage is better because it doesn't chew up power, whereas current does. We need to know about Ohm's law, which is V equals IR. V is for volts. V is for voltage in volts. I is for current in amperes or amps. And R is for resistance in ohms. As they say, a volt is what pushes an amp through an ohm. 1 volt is this is another way of saying the equivalent thing. 1 volt is the work done as one adds 1 joule of potential energy to 1 coulomb of charge. Ohm's law is useful, but it only applies to resistors. The inverse of resistance is conductance. So G equals 1 on R, where G is conductance measured in Siemens. Conductivity degrades, increasing resistance when temperature increases. It's not always true, but it's usually true. When temperature goes up, and the resistance goes up as well. If you have 2 points separated by a distance d with a voltage V between them, the uniform electric field E is given as V equals V on D, equals V on D. There are various strategies for making a resistor: carbon composition, carbon film, metal film, and wire wound. Many electronic components do not obey Ohm's law. Don't expect to use Ohm's law where it doesn't fit. It only works for resistors. We can extend the reach of Ohm's law with dynamic resistance. And the dynamic resistance is just the change in voltage divided by the change in current. And we learn about that in the experiments that we did. Usually the graph is given as I versus V, but if you flip it around this way, then the tangents are in ohms, which is why they've done it this way. So you can see here you've got the diode that goes here and then it goes off like that. So the same, you could say that the diode has this dynamic resistance at this point with that current and that voltage. Okay, Power is the rate of doing work. Okay. And components will have power ratings, so don't try to dissipate more power through a component than it's rated for. Formula for power in watts: P equals I times V, P equals I squared R, P equals V squared on R. To find the minimum resistance for a quarter watt resistor at 15 volts, then you just say a quarter watt equals 15 volts squared divided by R min, and then solve for R min, and you get 255 divided by a quarter equals 900. So 1 kilo ohm is close to the minimum safe value at 15 volts. Current measures charge per unit time, and voltage measures work per unit charge. The charges cancel, so the power is work per unit time. This is power. In this course, we rarely worry about power. Now here's Kirchhoff's two laws. We've got Kirchhoff's voltage law, KVL, and Kirchhoff's current law, KCL. The KVL states that the sum of voltages around a loop is 0. So there you go. And the Kirchhoff's current law, the sum of currents in and out of a node is 0. And that's what they call the algebraic sum, because the sign indicates direction in or out. And then there's the two cases here where you've got two resistances in series or two resistances in parallel. And then we can talk about what happens with the current. So the series current, the current's the same everywhere. For the parallel current, half of it goes this way, the other half goes this way, or in proportion to the resistors. So if the two resistors were the same, it'd be half and half. Otherwise, it's proportional. Series voltage, the total voltage is add. So the voltage across here and the voltage across here is the total voltage. And the parallel voltage is they're the same. So the voltage here and the voltage here. Applications of Kirchhoff's laws, series and parallel circuits, a couple of truisms probably familiar to you already. Now this diagram is important. You should understand that this is in fact a circuit. It comes full circle and connects back here at the power supply. So even though it doesn't look like a circuit when we drew it this way, you should know that it is a circuit, and it will start at the power and come back to the power. With resistance parallel resistors, the conductances add, and so that's the reciprocal of the resistances. And so you can come up, if you've only got two resistors that you're working with, then you can come up with an expression for the total resistance as R1 times R2 divided by R1 plus R2. And this gets more complicated if you add more resistors, but two resistors just looks like this. And we'll see our voltage divider looks very similar to this as well. So here's some typical cases. If you've got two resistors in and they're the same resistance in parallel, then it's just half of the half of R is the resistance. If you've got R and 10R, then the resistance is 91% of R, which is it's small, and we'll talk. We learn about that next. This one here, where you've got R and 2R, the result is 67% or 2/3 of R. This is useful. So when you've got resistances in parallel, the small r dominates, which is what we saw up here with R and 10R. This R dominates. It makes it like 0.91 R. So in parallel, the small r dominates, and in series, the large R dominates. And that's what this says here. In a parallel circuit, a resistor much smaller than the others dominates, and in a series circuit, the larger resistor dominates. So now we're gonna the first circuit that we made. Well, we've done this already, of course, was the voltage divider. And there's a note here just on potentiometers, which are the variable resistors that we use. When using a potentiometer as a variable resistor, it's a good idea to tie one end to the wiper. The wiper is the bit in the middle that connects to either side. This means that if the wiper comes loose, the maximum resistance is seen instead of an open circuit. This can be important as you probably haven't tested your circuit with an open circuit resistant from this component. So just get in the habit of tying off one end of your wiper on your potentiometers if you're using them as a variable resistor. So here is our first voltage divider. You can see that the it doesn't quite fit, does it? All right, I'll have to fix that. For now, just bear with me with these broken graphics. I can fix that. I'll fix it later. So this video is going to show all the broken graphics. Okay. Okay. So a voltage divider to analyze. So there's three ways to analyze this circuit. So the first thing they do is think about the current through the whole thing. So calculate the current and then and go through all this process of figuring out what the voltage is based on the current. So the second method, you just take that as given, that the current's the same, which means it cancels here and here. And then this expression V out equals V in times R2 on R1 plus R2. That's equation 1N1, which is going to be important to us. It says here you will use formula 1N1 fairly often. And the third method, say to yourself in words how the divider works. So you can muddle through to saying, since the currents in top and bottom are equal, the voltage drops are proportional to the resistances. Later, impedances, a more general notion that covers devices other than resistors. So in this case, where the low resistance makes up half the resistance, it will also show half the total voltage. Okay. So next we need to think about what we do if someone comes and attaches a load to our circuit. The first way, they call it the tedious method. So model the two lower R's as 1 and calculate V out for the new voltage divider. So that's where you take these in parallel and then figure out that that's 5K and then calculate V out for this new divider that's called 5K now that you've incorporated the load and the bottom leg of the resistance of the previous divider. But then they show us this better method. It's called Thevenin's model, and you use the model to calculate the Thevenin voltage and the Thevenin resistance. So note that load is not part of the Thevenin model. So you just ignore the load, and the Thevenin voltage is just what V out would be if the load were not attached, and the resistance is just R1 in parallel with R2. And this is this is Thevenin, the Thevenin model, perfect voltage source in series with output resistance. There you go. Thevenin's good idea. Model the actual circuit unloaded with a simpler circuit, the Thevenin model, which is an idealized voltage source in series with a resistor. One can then see pretty readily how that simpler circuit will behave under various loads. Thevenin voltage is just the open circuit voltage, the voltage when nothing is attached, that is with no load. Of course, when you attach a load, it affects the voltage, so it's important that you do this without attaching a load. The Thevenin resistance can be formulated as the quotient of the Thevenin voltage divided by the short circuit current, which is the current that flows to ground if you simply short the output to ground. But don't do that. In practice, you won't find RThev by shorting the output to ground, and doing so can be dangerous, so don't do that. So the shortcut calculation of the Thevenin resistance given in a certain diagram, the fastest way to calculate Rthev is to see it as the parallel resistance of the several resistances viewed from the output. So this is the output here. This formulation assumes that the voltage sources are ideal. Incidentally, when they are not, we need to include their output resistances. For the moment, we ignore this complication. So there's our Thevenin voltage. It's V in times R2 divided by R1 plus R2. And the Thevenin resistance is just R1 in parallel with R2. So you start at this point and look back into the circuit and you see this parallel circuit. Now here they go on to try and explain it, and honestly I read this, I don't understand it. Still, let's read it together. The shortcut shown in Fig-1N.32 asserts that the Thevenin resistance is the parallel resistance, but this result may strike you as a little odd. Why should R1 going up to the positive supply be treated as parallel to R2? Well, suppose the positive supply was set at 0 volts. Then surely the two resistances would be parallel, right? I don't know, maybe. Or try another thought experiment. Redefine the positive supply as 0 volts. It follows then that the voltage we had been calling ground, or 0 volts, is now minus 30 volts, to use the number from figures 1 and 16. In this case, it seems clear that the upper resistor to ground matters. The lower resistor, R2, going to minus 30 volts now, is the one that seems odd. But the circuit doesn't know or care how we have chosen to define our 0 volts or ground. The point of playing with the definition of ground is just that the voltages are at the far end of those resistors seen from the output do not matter. It matters only that those voltages are fixed. Note, later we will relax this requirement too. Thevenin's model works as well to define the output resistance of a time-varying voltage sources as it does for a DC source. Frankly, that didn't help explain it to me at all. I don't understand the justification. I understand what to do. I know how to treat the resistors in parallel. I just don't understand why they connect at the powers. I don't get it. Anyway, maybe if I keep throwing myself at it, eventually I'll understand. Okay, or suppose let's take a different divider designed to make the numbers come out nice with Vn of 20 divided by two 10k resistors. To discover the impedance at the output, do the usual experiment. Okay, so now we do something that I kind of understood a bit better. A general definition and procedure for determining impedance at a point. To discover the impedance at a point, apply a delta V and measure a delta I. The quotient is the impedance. So the circuit in figure 1N.33 is the small signal or dynamic version of Ohm's law. In this case, 1 milliamp was flowing before the wiggle. Actually, I'm just going to take a quick break and I'm going to try and fix up these graphics. I'll be back in a minute. Okay, I'm back. Sorry about that, but I fixed the graphics you see here. They fit inside their boxes again. So as we were saying, this is the general definition and procedure for determining impedance at a point. Apply a change in voltage and measure the change in current. And then you can calculate the impedance as the quotient of those two values. In this case, it's 5K. Here are the two circuits. This is the circuit we start with. And then in this circuit, we add the extra 1 volt in here. And we calculate the change in current. Rationalizing Thevenin's result parallel R's. Any non-ideal voltage source droops when loaded. How much it droops depends on its output impedance. The Thevenin equivalent model with its Thevenin resistance describes this property neatly in a single number. So the Thevenin resistance is the output impedance. And then we asked ChatGPT the question, are output impedance and Thevenin resistance the same thing? And the short answer is yes. In practice, they're the same concept. And it goes on to talk about that in greater detail. But the takeaway is that the output impedance is the Thevenin impedance. And when you're only dealing with DC and resistive cases, then the Thevenin resistance is the same as the output impedance. So, applying the Thevenin model, first let's make sure Thevenin had it right. Let's make sure his model behaves the way the original circuit does. We found that the 10K divider from 30 volts, which put out 15 volt when not loaded, drooped to 10 volts under a 10K load. See Fig-1N.32. Does the model do the same? So here's our circuit with its load, and then here's the Thevenin model with the load. And yes, the model droops to the extent the original did, down to 10 volts. So it's 10 volts here and it's 10 volts here. What the model provides that the original circuit lacked is that single value, the Thevenin resistance, which expresses how droopy or stiff the output is. Then we asked ChatGPT another question. If the output impedance measures how stiff or droopy an output is a higher output impedance more droopy or more stiff? And the answer is more droopy. So if you've got high output impedance, you'll have a more droopy output voltage. Higher output impedance equals less stiff. The output voltage sags more under load. And then there's some numbers there from ChatGPT. So if someone changed the value of the load, the Thevenin model would help you to see what droop to expect. If instead you didn't use the model and had to put the two lower resistors in parallel again and recalculate the parallel resistance, it would take you longer to get each answer, and you still might not get a feel for the circuit's output impedance. All right. Suppose that we try to measure V out at the output of each divider. If we measured with a perfect voltmeter, the answer would be 10 volts. And then they asked the question, is it 10.000 volts or 10.0 volts? And the answer is it could be 10.0 volts, but it could equally be a bit less than 9.9 volts or a bit more than 10.1 volts. If the 20 volt source were good to 1% and we use 1% resistors, we should not expect perfection. Now here we get to where we did our first experiment, which was with okay, so if we perform the measurement, we see the effect of loading by Rn of our imperfect lab voltmeter. So this was the first experiment we did, and we used the analog meter to measure the output voltage for the cases where the resistances were 1K, 10K, or 100K. And we got the and we noticed that the loading was obvious when we got to 100K using the analog voltmeter. And so the meter shows us eight parts in 10 across the dividers are Thevenin. Oh yes, I see. So when we get this this measurement here at 100K, and we measure here, and it says 8, then that's 8 volts across our internal resistance, but it means that there's 2 volts across here. So the meter shows us 8 parts in 10 across the 8 parts in 10 across the dividers. Call it R out. We must be dropping the other 2 parts in 10. The relative sizes of the two resistances are in proportion to these two voltage drops, 8 to 2, which is 4 to 1, which means that the Thevenin of the resistance of the voltmeter is 200k. Okay, so yeah. Oh, I see. Of course. So the I'm gonna need to take a break. Sorry about that. I'm back. So I must say I'm really exhausted. I'm just going to try and get through this, get this video out there. I've got to go and get some sleep. It's only Tuesday and it's already been a mammoth week. Anyway, look, it's 8 volts, 8 volts across the output resistance. We're dropping the other 2 volts across the voltmeter, which means that the proportion is 8 to 2, which simplifies to 4 to 1. And since that's 50, we multiply by 4, we get 200k, and that's the 200 kilo ohms is the internal internal resistance of the VOM. And there's a spec on the voltmeter, and it says 20,000 ohms per volt. And given that we have 10 volts, it's to 200,000 ohms, which is 200k, which is what we saw. There's some notes here about how the internals work for the VOM, the analog meter and the digital meter. Basically, the analog meter is a current sensor, and the digital meter is a voltage sensor, so they work differently. The voltage sensor disturbs the circuit less than the current meter does. The VOM specification of 20 kilo ohms per volt describes the sensitivity of the meter movement, the guts of the instrument. And then I asked ChatGPT the question, please explain a meter movement to me. So it does that. Meter movement is a noun. It's not a verb, and it tells you about how that all works and gives you some numbers about how to calculate these different parts. Then finally, we get up to the next part of our experiment, which is where we do the same thing again, but this time with our digital voltmeter, and we up the values quite a bit. So we start at the 100k, which is where we finished with the analog meter, but then we go to 1 meg and 10 meg. And we did those experiments, and we calculated this table of values. We actually had to measure these parts, then we calculated the rest of them, and we found that the DVM was a much better, here it is, a DVM is a better voltmeter, at least in its input resistance. As a current meter, the DVM will fare no better than the analog meter, and both of them drop a quarter volt full scale. The question for ChatGPT is it generally better to have a low input impedance and a low output impedance and a high input impedance? And the answer is yes. For voltage mode signals, you usually want a low output impedance at the source and a high input impedance on the load. But that's qualified for voltage mode signals. If you want to do power transfer, then you want to do impedance matching. We'll probably cover that eventually, but this particular note is just from ChatGPT. So I'll look at that. The math hangs over the edge. Interesting. So now we're actually up to the point. These are the new notes. I've been working on them this week. So we have a little digression on ground. We want to talk a little bit about ground. So the concept of ground, also known as earth in different parts of the world. The Americans call it ground. The British call it earth. I don't know what we do in Australia. We probably say earth ground. Who knows? Anyway, it's ground and earth, and it can apply in different senses. So the local ground, which is usually what we care about, is a common point in our circuit that we arbitrarily call 0 volts, and only rarely do we care if this point is connected to the earth ground, which we'll discuss next. all points labeled local ground are electrically connected to each other. So it's important to remember that that ground symbol, everywhere it turns up, it's just actually one point. All of those points are connected together. Now the earth ground, these are wires connected to a metal pole that has been driven into the ground of planet Earth. Sometimes local ground is connected to earth ground, such as the ground clip on the scope probe. When local ground is connected to earth ground, you need to be careful not to attach supply voltage. And there's a picture of earth ground over here. Let's have a look at that. So this is the ground wire, and this is the pole that's gone into the ground. So that's literally how an earth or ground wire gets installed. And then when I was doing the research for this, I found there's also sometimes signal ground, and it has its own symbol. A reference point in electrical and electronic circuits typically represents a zero potential voltage level, serves as a common return path for signals, and is crucial for accurate measurements in some devices. And then we go, sometimes, but not always, local ground, earth ground, or signal ground are connected to each other. There are schematic symbols to represent local earth and signal ground, but they are not used consistently. Sometimes chassis ground is connected to local ground, and sometimes to earth ground, and sometimes to both. So chassis ground, you got to be careful. You could see this circuit, this diagram could mean chassis ground, or this diagram could mean chassis ground. So basically it's a big mess. But this is local ground, this is earth ground, this is signal ground. But it's not always going to be that way. Depends on the publication and their conventions. Anyway, that brings us to the end of the notes for today. And no experiment today just because I've run out of time, but we'll aim for an experiment next Tuesday when we keep on keeping on. So let me throw over to the farewell cam and we'll wrap up.
And that's a wrap. So just some notes today, just some revision of the stuff that we'd already seen. A little bit of information there on ground, which I've been writing up. So I'm glad that we do this revision because I forget week to week about what we were doing. Hopefully by the time we get to the end, I'll know it all and remember it all. So yeah, I'm gonna wrap up the video there. There's a whole lot of other stuff coming out this week. It'll be another week. We'll do another one of these videos, and yeah, I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.